If you recall, last week we talked about these two integrals, 1 over x squared plus 1 and x over x squared plus 1. And so these are going to be two core integrals, and what we want to do is build on these. We want to see why for rational functions, all we need are these two. For rational functions with irreducible quadratic denominators. So we have the integral of 1 over x squared plus 1 is arctangent of x plus c. And the integral of x over x squared plus 1 is a half natural log of x squared plus 1 plus c. We stopped here. We don't have to go any further with the numerators. We started off with the numerator of degree 0 and a numerator of degree 1. If the degree of the numerator is greater than or equal to 2, then we're going to use long division to break off a polynomial and a fraction where the degree of the numerator is less than 2. So if the degree of the numerator is greater than or equal to 2, then use long division to rewrite the integrand as a polynomial plus a fraction. And the fraction parts will either have a degree 0 or a degree 1 numerator. So we only have to worry about 1 over x squared plus 1 and x over x squared plus 1. These are the examples that we looked at last week. We can use long division to write it in this mixed number format rather than an improper fraction format, where we just integrate the polynomial and then the fraction part is one of these. Even if it's a combination of both of them, we can still just separate it out into two. So for example, let's see. So these are the examples we did last week. If I have a combination of these two, we're going to use the fact that integration is a linear operator and just separate it out. So if we wanted to integrate, let's say 3x minus 5 over x squared plus 1 dx. I have 3 copies of an x over x squared plus 1 minus 5 copies of 1 over x squared plus 1. And those are the two building blocks that we set up last week. So x over x squared plus 1 is going to be a 1/2 natural log of x squared plus 1. And integral of 1 over x squared plus 1 is arctangent, so minus 5 arctangent of x plus c. So if we had, as long as we have a linear numerator and an irreducible quadratic denominator, this is how we can proceed. We just need these two. If our numerator is greater than degree 2, so let's say, for example, I'm going to reverse engineer a problem. I want the degree of the numerator to be greater than that of the denominator. So I'm going to come up with what I want the answer to be. I want 2x, let's say plus 1 plus 3x minus 5 over x squared plus 1. This is what I want you to integrate, but I don't want to give it to you in this form. I want to mess with you algebraically. So I'm just going to take this mixed number and I'm going to write it in improper fraction format. So this is equal to 2x plus 1 times x squared plus 1 plus 3x minus 5 all over x squared plus 1. Now this looks like I'm doing something weird and foreign in algebra, depending on how deep your algebra class went. But this is the same thing we do if we want to take a mixed number and write it as an improper fraction. If I have the mixed number 2 and 1/3, I get an improper fraction by taking 2 times 3 plus 1 all over 3. Just kind of go around this way. And that's the exact same thing we did over here. X squared plus 1 times 2x plus 1 is equal to 3x plus 3x minus 5. Now I'm just going to combine this numerator, and I'll have the problem that I actually hand you. So it's going to have to FOIL here. So I'll have 2x cubed plus 2x plus 1x squared plus 1 plus 3x minus 5. So the problem that I actually hand you is going to be 2x cubed plus x squared. 3x and 2x is plus 5x minus 4. I just put that together in the same way that 2 times 3 is 6. 6 plus 1 is 7/3. So now if we want to integrate this rational function, we notice that the denominator is x squared plus 1, irreducible quadratic. We notice that the numerator is of degree greater than 2, greater than or equal to 2, but in this case, greater than 2. So let's turn the page and pretend that that's where our integral started. So here's what the problem looks like if we're starting off, and I want you to do some algebra on this. You would notice that the degree of the numerator is greater than or equal to that of the denominator. Therefore, you're going to use long division to write it as a mixed number. You're going to get a polynomial plus some fraction, and that fraction, the numerator of that fraction will be of degree 1 or 0. So here is where we break out our long division skills. What's triggering this activity is the fact that the degree of the numerator is greater than or equal to that of the denominator. So how many times can I subtract x squared from 2x cubed? I've got to make them like terms. So I'll need at least an x. And I'll need a constant of 2. 2x times x squared is 2x cubed. 2x times 1 is plus 2x. And then we'll have to subtract. I'm just following the same plan that we always use when we're doing long division. How many times can I subtract the denominator from the numerator? And in this case, we start off with that first term. How many times can I subtract x squared from 2x cubed? I can do that 2x times. And then we need to subtract. 2x cubed minus 2x cubed is 0x cubed. That's what we wanted to happen. We want that first term to go away. X squared minus nothing is x squared. 5x minus 2x is 3x. And negative 4 minus 0 is negative 4. Now we just repeat the question. How many times can I subtract x squared from x squared? And I can do that 1 time. So 1 times x squared is x squared. 1 times 1 is 1. And then we subtract. X squared minus x squared is 0. That's what we wanted to happen. 3x minus 0 is 3x. And negative 4 minus 1 is negative 5. I can no longer subtract x squared from the remainder, or 3x minus 5 is going to be my remainder, because I can't subtract x squared without writing fractions. So instead of integrating my original rational function, I'm going to integrate 2x plus 1 plus the fraction 3x minus 5 over x squared plus 1.
Sorry, Professor, I have a quick question. Why is it plus 1? Shouldn't it be minus?
I can subtract x squared from x squared one time. 1 times x squared is x squared, and then we subtract. If I made it a -1, then I'd have a negative x squared, and x squared minus a negative x squared would be 2x squared, which is not what we want. We want these to cancel out. And that's what goes up here.
So why is it 3x minus 5? Shouldn't it be minus 3 instead? If you're adding
-4
positive 1?
minus 1. We're not adding, I'm subtracting.
Oh, okay.
-4 minus 1 is -5.
Oh, got it. You're right.
Now I have the fraction part is degree 1 in the numerator. And so now we can just integrate a term at a time. So we integrate the x squared. Integral of 2x is x squared. Integral of 1 is x. The integral of 3x over x squared plus 1 is the 3/2. This is just from the previous page. So here we can integrate this rational function with this x squared plus 1 denominator, and we only need to worry about numerators that are degree 1 or degree 0. Because if the degree is 2 or more, we can use long division, and that separates off the polynomial. We go from improper fraction to a mixed number style, and then we can just go a term at a time. This raises an important question. What if it's not x squared plus 1, but x squared plus something other than 1? So what if we have an x squared plus 9 instead of an x squared plus 1? Or in general, what if it's x squared plus a squared? I'm going to cheat a little bit and say it's better if this is a perfect square. But we're going to want to see that show up in our calculations. So in general, this is a 9, and down here is an a squared. So what if I change that to a 9, for example, instead of a 1? So we might be thinking, man, I really wish instead of saying plus 9, it said plus 1, because then I could use my my base model from the previous page. How is that 9 going to affect things? I would rather that plus 9 said plus 1 instead. So that's what we're thinking about. Instead of a +9, I wish this said +1. So the thinking is this: I wish this was a +1 so I could use my base model from the previous page. Instead of 1 over x squared plus 9, I wish it said 1 over x squared plus 1. So we're just going to make that happen. I want that +9 to say +1, so I'm going to factor a 9 out of this polynomial. So I wish that was a +1, so I'm going to make it so. I'm going to factor a 9, and that'll leave an x squared over 9, but it'll say +1. So all I did was factor a 9 because I wanted that to say +1. So I'm going to factor out a 9 because that's just a constant and I can pull that out whenever I want. So what I'm looking at is a 1/9 integral of 1 over x squared plus x squared over 9 plus 1 to x. Now we got that +1. So we factor out a 9 to make it so. But now we're like, oh, hold up. We've got this x squared over 9. Now that's a problem because my previous one was just x. I wanted x squared plus 1, not this friggin' x squared over 9 plus 1. We got the +1, so that's good, but we've got this x squared over 9. But that's no problem at all because we're just going to do substitution. So I'm going to take this x squared over 9 and I'm going to make a substitution. So I still got this 1 over 9. I'm going to read x squared over 9 as x over 3 squared. I'm going to write the x squared over 9. I'm going to read it as x over 3, and then we'll make a substitution. So w is going to be an x over 3. dw will be a 1/3 dx. And so 3 dw is the dx. I'm just going to replace the dx with a 3 dw, and then I'll be able to integrate. So now this is going to be a 1/9 integral of 1 over w squared plus 1 . And instead of dx, I have 3 dw. And now I'm looking at my base integral, 1 over w squared plus 1. There's a 1/3 because it's 3 times a 9th. So 3/9 is 1/3 integral of 1 over w squared plus 1 dw. Now I can use the base model that I had from the previous page. The integral of 1 over w squared plus 1 is arctangent of w plus c. I still got this 1/3 out in front. And then I just have to replace my w with x. So I have 1/3 arctangent x over 3 plus c. So by changing the +1 to a +9, I ended up with a 1/3 coefficient and an arctangent of x over 3. So in general, the integral of 1 over x squared plus a squared is 1 over a arctangent x over a plus c. Now we've improved on our 1 over x squared plus 1. So now it could be 1 over x squared plus a squared. Now, this is the only one where that really matters. So notice that if the numerator is x, then it's just a substitution problem, and it's not going to matter what the a squared is. So notice that if I have, let's say, x over x squared plus 9, now we don't care. The +9 is not going to be any different than a +1 because we made the substitution w equals x squared plus 9, and the +9 is not involved in the dw. So dw is 2x dx, and so a 1/2 dw is x dx. So this is going to be the integral of 1/2, or 1/2 the integral of 1 over w dw. So we still have a 1/2 natural log absolute value of w plus c, and then we can replace the w. 1/2 natural log of x squared plus 9 plus c. So the important thing to note about this denominator is that this denominator is irreducible over the real numbers. X squared plus a squared is quadratic with complex zeros. So this raises the next question. What if there's an x term in our denominator? I still only need those two original ones. 1 over x squared plus a squared and x over x squared plus a squared. I still only need those as my base. If the numerator is too big, I use long division, and the fraction part will have a degree 1 or degree 0 numerator. And now we've solved the problem of x squared plus a squared instead of x squared plus 1. But what if there's an x in the denominator? What if there's an x term in the denominator? And the denominator is still irreducible. So for example, what if I wanted to integrate 1 over x squared, let's go with minus 2x plus 13. Oh, not 2x, let's go with, oh, let's just change that to a plus 10. There aren't real factors of 10 with which I can make whose sum is -2. So this is still irreducible quadratic. Here's the problem. This is the change from the previous problems. It's minus 2x. There's still an algebraic response to this. I want this to look like 1 over w squared plus a squared. I'm going to substitute my way into 1 over w squared plus a squared so I could use my new in general arctangent version of things. And all we're going to do is complete the square. Hit this with the algebra stick. We're going to complete the square. And then substitute. So I'm going to rewrite x squared minus 2x plus 10. So I've got x squared minus 2x plus 10. I think about what I need to complete the square. X squared minus 2x. To complete this square, I need plus 1. And if I take plus 1 away from the plus 10, that leaves behind a plus 9. So I'm just splitting up the plus 10 into a plus 1 and a plus 9. The reason for the plus 1 is that x squared minus 2x plus 1 is now a square. So I can write that as, inexplicably switching colors, I can write that as x minus 1 squared, and then I still have this plus 9. And now I can substitute my way into my, in general, arctangent. So integrating 1 over x squared minus 2x plus 10 is equal to the integral of x minus 1 squared plus 9. Now we can just do a substitution and use our general arctangent. So w is going to be x minus 1. dw is just dx. Oops. They're the same, but they're not substituted yet. So I'm still integrating a 1 over something squared plus 1, or 1 something squared plus 9. But instead of x minus 1, that's w. And instead of a dx integral, this is now a dw integral. The integral of 1 over w squared plus 9, I could use my new general arctangent version of things. And so this is going to be 1/3 arctangent of w over 3 plus c. Then all I have to do is replace my w with my expression in x. So 1/3 arctangent x minus 1 over 3 plus c. One of the things that we want to note here is that when I say irreducible quadratic, I mean quadratic with complex zeros. So that's the important thing to note about this still irreducible part. This means complex zeros. If the denominator has real zeros, then we do something different. But we just want to see how algebra gets us a lot of mileage out of knowing the integral of 1 over x squared plus a squared and x over x squared plus a squared. Now, are these procedures that you're going to be following when you in your future career as a fill in the blank? I'm not allowed to look to see what your future career is going to be. Most definitely not. If you're in your job and you're not a math teacher and you're about to do stuff like this by hand, you're probably about to get fired. Actually, this takes kind of a long time, so you're going to be fired in like an hour or two. You're going to go, what are you doing this by hand? We have all this computing power. Why are you doing this by hand? And then you'd be like, oh, because I want to murder trees. And then you're coming to be like, oh, ah, well done. We also want to murder the trees. Then you all high five each other. And go buy a twin turbo V12. I don't know. I'm not allowed to look into your futures. Although I do see a twin turbo V12 for one of you in the future. So enjoy. But we're getting a lot of mileage out of those two core things, the 1 over x squared plus 1 and x over x squared plus 1. And then we're just using algebra to funnel everything down to those two. We just use algebra to funnel everything down to those two. This is what we like to do in math. The three great tricks of mathematics are to add 0, multiply by 1, or change your variables to easier variables. Rewrite the conditions of the test, Kirk style. Any questions? On one hand, Kirk is clever for rewriting the test so he can win. On the other hand, talk about missing the point of the test. Because he was just trying to get an A on the thing so he could win the scenario. Because he doesn't believe in the no-win scenario. But we see the evolution of this when Picard says, sometimes you can do everything right and still lose. Which kind of refutes Kirk's whole premise. There is a no-win scenario. How do you deal with it? Kirk has to cheat. This is a severe character flaw. I applaud his creativity, but that's a character flaw. I'm not saying that we should accept. You don't have to be happy about it, but to cheat to circumvent that, I think is kind of a character flaw. And it reduces the exercise to just the test. It'd be just like if I gave you a test, if they gave you a test here in this calculus class. Because of the format of the test I'm using, you could cheat to circumvent the test to make sure that you win the scenario and get the correct answers on the test and get 100% and get an A. But why? That's missing the entire point of the exercise. Do the problem, get it wrong, take your second chance at it. Get it wrong, take your third chance at it. Keep doing that until you get the right answer. Now you could argue, in the end, cheating on the test made him a Starfleet captain. And so didn't he win? It's like, well, yeah, he did. At what cost? At some kind of real cost that can be measured? Probably not. In the same way that you could cheat on any calculus problems that I hand you. You can win the scenario, but at what cost? You know what I mean? Incidentally, when you copy and paste, it is super obvious. Every time you just look something up and copied and pasted, even if you just copied and wrote it down, I know. I can absolutely tell. All right. Any questions? Comments? Snide remarks? In the end, y'all will have A's. Some of you got A's on your own accord. And I know some of you, I'm just evaluating, you know, what the tutors at the STEM Center did. Or what is it Chegg? Yeah, what that website said, or what Wolfram Alpha did. And Wolfram Alpha got an A. And maybe no one else will know, but you will. Anyway, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.